Hi and welcome to this invited talk. Okay, so what we're going to do now is lessons from 3 decades of research into learning and reasoning with relational probabilistic models. This is not meant to be a survey, so I apologize for anyone whose work I miss out on. It's more just things that everyone should know about this area. Even some people in the field may not know a lot of this, so hopefully it's going to be of interest to everyone. I found an interesting quote by Steven Pinker. Maybe you could pause it and have a look at the whole thing, but for now, the mind is a neural computer fitted by natural selection with combinatorial algorithms for causal and probabilistic reasoning about plants, animals, objects, and people. And it's this probabilistic reasoning about plants, animals, and objects and people that we're going to talk about in this talk. All right, so we're going to first of all start talking about what are relational probabilistic models. We're going to talk about learning knowledge graphs, learning general knowledge, so-called lifted graphical models. Then we're going to talk about lifted inference, identity, and existence uncertainty. So I'm mainly going to talk about things for which there aren't really good surveys that I know about. Okay, this is the motivation. So AI studies what agents should do. And agents act, and acting is gambling. And agents who don't use probability will lose those who do. So if you want to gamble, you should use probability. And the other part is no prediction is certain. Never believe anyone who gives definitive predictions. If someone predicts you'll be run over tomorrow, do not believe them, do not act on that. If someone predicts you will not be run over tomorrow, do not believe them, do not act on that. Okay, so it's much better for people to give definitive prediction, to give probabilistic predictions, so that we can then make proper decisions. But also the world can be modeled in terms of entities with probability, properties and relations. To this field, it's probably pretty common, but lots of things in machine learning and probabilistic reasoning have features and random variables, and they often have internal structure, and we'll look at that. So one of the ways of thinking about this is we start off with propositional logic, and we end up with probabilities, measures over possible worlds, we get probability. Or we end up with relations and logical variables and quantifications, we get predicate logic. And if we add both of them, if you add measures over possible worlds and relations and logical variables and quantification, we get relational probabilistic models, and that's what we're going to talk about. All right, so let's talk about relational models. So most introductions to AI and machine learning, you start with learning from relations. So here's a typical example. You have an example and you want to predict whether the user reads or skips a news item based on whether the author is unknown, whether it's a thread, whether the length is short or long, whether they're reading at home or work. And you like to build a decision tree or a neural network. But most databases are not like this at all. They have values with meaningless names. That's what we call relational models. So what makes relational models in machine learning special is the values as meaningless names. For example, student number or product ID or user ID or movie ID. So here's an example of a movie, something from the Movie Lens 100K. It's got users, movies, rating and timestamp, and 196 is just a meaningless name. So this is just a meaningless name. If we swapped 196 and 186, numbers everywhere, the database wouldn't change. So the names can be changed or exchanged with exactly the same meaning. So if I swap the meaning around, there's no meaning to these numbers. They're just meaningless names. They're just meaningless names. Okay. Now, this is something that probably most people here know. So there are lots of different ways of representing facts. So for example, how to represent pen 7 as red, you could write red pen 7. But you can't ask what is the color of pen 7. If you do that, you could write this one. Color pen 7 red. It's a bit like the top of like red pen 7, but you can ask what is the color of pen 7. Okay, and you can go do this same trick again. You can ask what property is pen 7 as color and red, because then you can ask what property of pen 7 has value red, and the answer is color. And if you don't need to do this again, because all you need is prop. So it turns out that the single relation is all you need, and so you end up with triples. So pen 7, color and red is all we need is in terms of triples here. So all relations can represent in terms of triples. So you can represent arbitrary tables in terms of, so if you have a row, this property here and a value Vij, it can be represented as a triple Ri of P J of Vij. And Ri is either a primary key or it's a reified entity. So it's either something we're going to make up in the world, a new name, or it's a primary key. So, and examples of reified entities are a booking. So we might have a booking, a marriage, a talk, a lab report. So lots of different examples of reified entities. And then these triples are the only things we need. So we'd have triples, semantic networks, entity relationship models, and knowledge graphs. And the only thing that's new about knowledge graphs is the fact that people are now trying to learn these. And so when you try to learn things, you often simplify things than they are before. So we're not going to necessarily look at the most detail of things. Unfortunately, lots of knowledge graphs convert to triples naively. So lots of them do projecting onto pairs and it loses information. So as an example, Air Canada flies from New York to Vancouver. Air Canada flies from Vancouver to Los Angeles. So both of these are two triples. Air Canada flies from New York and Air Canada flies to Los Angeles. However, Air Canada does not fly from New York to Los Angeles. The information about flights is lost, and if you project onto pairs, you lose information. And so maybe it's harder or maybe it's easier to reason about it, to learn or reason about it, but in fact you've lost information. So FB15K is a knowledge base that's used in research papers. It contains some test cases like Jade North plays position defender, and Jade North plays for the Australian national team, the Socceroos, in case you didn't know. Real Zaragoza is a football club, has a position called defender. And these are queries in here. What they try and do is predict one position in the tuple given to others, and it varies widely in difficulty. So what I'm suggesting, first rule of machine learning, is to follow this and look at a knowledge graph before you use it. This is actually very enlightening to actually look and read through what this meant. It's actually hard to do it because you actually have to look up. It doesn't actually write Jade North. You have to look up from the name, the value, the meaningless symbol in here. You have to look up the name is actually Jade North. So I've actually simplified things here to make it readable. All right. Another thing to know is that there's lots of work in sort of natural language which try to talk about represent words as vectors. And you can do interesting relations like king minus queen is equal to man minus woman. So in fact you get king minus man plus woman is queen. So we can have the representation of queen can be worked out the representation from king, man and woman. So it's tempting to want to write these so-called translational models which are common. The Brussels is Belgium plus the capital of, and Washington DC is the USA plus the capital of. So Brussels is the capital of Belgium. And like to treat these as vectors and treat this as vector algebra. However, if you try to do this, this entails that the USA is Belgium minus Brussels plus Washington DC. And I'd like to challenge you. I could tell you everything you want to know about Belgium, Brussels and Washington DC, and I claim you won't know anything at all that's of interest about the USA. So although these seems tempting to try to do this, it's important to actually think about how entities and how relationships work. All right. So words can have simple meanings, but almost all entities are multifaceted and complex. All right, so now let's talk about how to actually go about learning knowledge graphs. So before, a bit of background that everyone should know, but hardly anyone seems to. So if you get the probability of H given evidence is the probability of H and evidence divided by the probability of evidence. We can divide it up like this. And now we can divide the top and the bottom by the probability of H and E. We get this. And we can actually write this in a way of putting in e to the log. And this works as long as there are no zero probabilities in here. And this ends up being the so-called the sigmoid of the log odds. So the sigmoid is 1 over 1 plus e to the minus x. And the sigmoid is what you've seen, is your friend you've seen from logistic regression on neural networks. And the odds is this probability of h given 1 minus h. So then what we do is typically the odds is a product. We typically try to give a multiplicative way of the odds. So then then you end up with a sigmoid of a sum, and that's actually called logistic regression. So it's typical to learn the probability of a Boolean feature. So if you look at the end value of a neural network, you typically have a sigmoid of a linear function. And if you want discrete features, it's the softmax. So the softmax is the sort of multi-valued discrete version of a sigmoid. So sigmoids are going to pop up all the time, and they're special because they really mean something about probability. All right. So if we want to learn a binary relation, so like likes, person, movies, so if you want to do this, what people recommend to do is this a model that says the probability of likes PM is this sigmoid of summing over a whole lot of features, as there's features of people and features of movies, and you're going to multiply these out. And this is actually called the matrix factorization models, where an embedding is a vector of feature values, and there's an embedding for each person and for each movie. And this is sort of the most common way to predict movie relations, particularly when you make just a binary relation in here. If you're predicting a real valued one, you can leave off the sigmoid and just use this and predict the real. But if you're predicting just a Boolean, a true false, then the sigmoid is appropriate. Okay, so now if we want to learn a triple, the head, relation, tail, then the obvious way to do it is just multiply three things together. Well, I think it's the obvious way to do it. Lots of other people don't seem to think this is obvious. So you end up with, there's now an entity, embedding for the feature. For the feature is corresponds to the embedding space, an embedding for H, an embedding for the relation, an embedding for the tail entity. Okay, this is called the Polyadic decomposition model from 1927. So there are two vector embeddings for each entity and one from each relation. And this, to me, is the obvious way to extend matrix factorization. It doesn't seem so popular because there's no good notation, but there's lovely notation for matrices. There's not such, nice notation for these tensors, for this tensor factorization. Okay, unfortunately, it doesn't work very well, and here's why. So if you have a person 123 likes movie M53 and M53 is directed by P534, then what happens is that there's two entities embeddings per entity. So the head embedding and the tail embedding. And this uses the tail embedding for M53 and this uses the head embedding for M53. And they don't interact at all. So you can't actually learn that someone likes movies that are directed by a particular person or a particular type of person. So you can't learn this. You can't learn this interaction amongst values to actually learn what someone might like. Okay. To solve this, there's a few solutions. So this you share the same embedding for the head and the tail. But unfortunately, this can only represent symmetric relations. We could do complex, as like this but you complex numbers, and the tail is the conjugate of the head embedding, so it sort of ends up being reasonably hard to interpret about what's happening. Simple is another one. We have an embedding for r to the minus 1, and then you predict both hr of t and t r to the minus 1 of h, and then the embeddings interact. And one of my favorite models is Simple Plus. It's simple but with non-negative entity embeddings. So this can represent arbitrary relations. We call this, it's fully expressive, but that really means it can memorize things. It doesn't mean it can generalize well. It has pointwise less than or equal to, for relations, corresponds to implication. So it can actually do implication, one property can imply another property. And it's easy to explain what it learns, and we'll try and do that now. All right, so here's this one. We'll look at just the positive version of polyadic decomposition. The sigmoid of these three values multiplied together. And we're going to assume these are above 0. I'm going to assume all embedding values are bounded. It turns out that's a reasonable assumption. And we consider this feature I, so this I value of this embedding. So you want this is close to 0 if any one of them are close to 0. So if any of them are 0, the whole product is 0. And it also happens for close. So if you consider feature I, then the product is much bigger than 0, and that's the ones that are going to matter. The ones that matter here are the ones that are much bigger than 0, or much less than 0. Ones around 0 are sort of irrelevant. But it's much bigger than 0 if the head embedding at this position I is the embedding for H is the head embedding for H is much bigger than 0. The relation value is much bigger than 0, and the value for the tail is much bigger than 0. They're the ones that matter. The ones that really make a difference are those ones where all three of them simultaneously are. So this feature I forms two soft clustering of entities. Those entities for which E0 of the entity is high, they're the ones that are going to be in the first argument, and those values for which E2 is high. And so these two products are high. So what happens is those entities in the first cluster, in this cluster, are related to those entities in the second cluster for any relation for which E of I is high. So what happens is that these ones, there's a soft clustering amongst the entities, and these relations pick out which soft clustering it's going to use. And negative values of EI of R provide exceptions to those rules. So there are rules and there are exceptions to them. And that's what it's learning. It's learning essentially clusterings of entities, and each relation sort of uses different clusterings. Can use clusterings of these. All right. Now let's suppose we want to create a model of who's friends with who. Okay. There are options. You can learn general knowledge, for example, transitivity, how males and female friendship works, how location affects friendship. We could learn specific knowledge about who's friends with who, which particular group of people are generally friends with each other. The specific knowledge will tend to be more accurate on that population. However, it doesn't generalize to different populations. You learn about different groups of people, and it's just assigning people to these groups we don't really give names to. The general knowledge will transfer better, but which is better depends on the goals and how we're measuring success. So ideally, we'd like to do both. We'd like to learn about specific entities and we'd like to learn general knowledge. But there are very few models that actually do this, that learn about specific entities, clusterings of entities and general knowledge. And it's an interesting challenge. All right. So one of the problems with it is that we're only providing positive examples. And so think about these following relations. Married to, where people are generally married to 0 or 1 people. Friend of, where people can have tens or maybe hundreds of friends, but knows about is very asymmetric. So there's some people who lots of people know about, and there's some people about who very few people know about, and some of the people who billions of people know about, and would get along with, well, maybe nearly everyone would get along with everyone else, except a few exceptions. So if you like to predict these, you're going to get very different answers. Okay, so all right. And so now what happens is now we want to evaluate knowledge graphs with positive information and sort of evaluate a prediction. So typically what we do is we ask for who can we predict who plays position defender. Jade North plays which position? Real Zaragoza has position what? And this what has position defender. And it's commonly used to measures such as the mean reciprocal rank, which looks at the ranking, takes 1 over it and averages it. The hit at 1, which says I get to predict one value and I'm going to work out where in my ranking does, I have a ranking, or hit at 10. So if my first 10 in my ranking, if I hit at 1, I get to make one prediction, and then I have to see, where does how accurate am I? Or hit at 10, so I get to make 10 predictions. My top 10 most likely, and how likely is it that the answer we're expecting is in the position. So first of all, there's a few problems with ranking. It's not good for answers for which there's no answer or many answers. Who's the Pope married to? It turns out that in none of these do they ever ask this question, because it's sort of the only ones they ask questions for are the ones that they already know, that they already have a value for. They're trying to find that value. Another problem is an oracle that knows everything about here, knows everything about football, does very poorly on ranking scores. So if you ask, Jade North, who does Jade North play position, it can probably should be able to tell you defense. But Oracle wouldn't know. It says, I'm thinking of a person who plays defender. Who is it? And the Oracle would be terrible at that one, right? So the Oracle here doesn't know how to answer this. And this one here, this soccer team has which position? Well, it has lots of positions, so it could actually just list all of them. It doesn't do well at rankings. So, and which team has, so every soccer team has position defender, but you're asked to enumerate them and order them and rank, then even an oracle doesn't do well. So you'd like to have a measure that an oracle does well. So another challenge we have here is how to actually evaluate predictions on knowledge graphs. So the challenge here is to design a good evaluation scheme. Log likelihood Sort of seems reasonable, requires knowledge of negations which we don't have. All right. Now, tensor factorization models work well for predicting relations, but they work terribly for predicting properties. Well, you might be surprised, but if you think about that, tensor factorization relies on a lower dimensional representation, and there isn't one for properties, right? So once you have a property of this, there isn't really a lower dimensional representation. So imagine, for example, we have a data set like the movie lens, and we like to predict age, the age of person P, and the rating of person P on movie M. And so what we can do is, if we try to do the tensor factorization models, one of the embeddings for each person, you just memorize the age. You can't do, there's no generalization. You end up with too many parameters in here for doing this. So trying to predict age, we can actually just memorize it. There's too many parameters. So if you want to do this, you need to predict age using just the properties of movies and ratings. What's the properties of movies that they've rated? But to do this require aggregation. So there's lots of movies and ratings that are available. We have to somehow work out how we can aggregate all of the movies that they've done together. So some of them provide implicit aggregation. I'll talk about that in a minute. And some we can use, they say, well, you can use whatever aggregation you want. Unfortunately, we never know what aggregation we want. So we need some better models of aggregation to actually start thinking about what aggregation is appropriate for these. If we go beyond triples, so that was all just about knowledge graphs. We go beyond triples with relations with multiple arguments, well, we could convert them to triples by reifying. However, this doesn't work because the reified entities have very few data points. Eventually, the number of data points of a reified entity is the number of arguments of the original relation. And we could design embedding models that work directly with original relations, or we could let them be inferred from other relations. And so there's actually very little work on here, so it's actually a very interesting area to work in. All right, so now let's look at a more common model. Another common model is the lifted graphical models. So here's an example of doing it. So I have this database of students and courses and grades, and I want students S3 and S4 if you look at this S3 and S4 here, you notice that they have the same average on the courses. This is the only information. Which student would you expect to do better on C4? Well, it turns out that from this database, you can actually work out that one of course C2 or C3 is more difficult than the other. Okay? And so now we'd like to model that. One of the things we can model that is you model this in terms of a graphical model that says the grade of a student in a course depends on the intelligence of the student, or maybe how much the student works, and the difficulty of the course, right? And the grade of student in C2 depends on the difficulty of course C2, as does the grade of student 3 on course C2. Okay? And what we're going to do is we're going to end up having these models, but we're going to share the parameters in here. So we're going to say this is the table that we're going to use for all S and for all C. So these values, these student and course, are going to correspond to logical variables. And here's the grade is either going to be A, B, or C. But this model is going to be shared for all students and all courses. They're all going to share the same parameters. And here we could actually build this in our favorite Bayesian toolkit. And we're going to find out that students, from these things, that students S3 you'd expect is more likely to get an A, and student S4 is down here is more likely to get a C. Okay, and we can actually draw this in terms of plate notation, which is a nice way to draw this. And these S and these C's become logical variables that represent students and courses. And a set of entities of a type we're going to call a population. And these I of S are parameterized random variables. And there's a grounding. So now we're going to ground these out. For every student, there's a random variable of the intelligence of the student. For every course, there's a random variable that's the difficulty of the course. And for every SC pair, there's a random variable of the grounding of the student, the grade of the student in the course. And all these instances are going to share the same structure and parameters. And with 1,000 students and 100 courses, there are 1,000 I of S variables and 100 DC variables and 100,000 grade SC variables for 101,000 variables, but there's only 10 parameters in here, even representing this in table form. Now, one of the problems we end up having this is how does a relation affect by other relations, so-called aggregation. So the common ones we're going to do it is weighted formulae. So the undirected variant here is Markov logic networks, and the directed is relational logistic regression. There's other ones. You can do existential quantification. So in terms of logic programs, you could actually have a model here, the independent choice logic or problog is a directed model that uses existential quantification for aggregation like logic programs. And MLNs and RL are identical when everything else is observed, when you've observed everything else. I should also note that one of my other favorite ones is relational dependency networks, so directed models that induce a Markov chain. And that sort of has lots of interesting properties in here that's not necessarily in this framework. So here's an example of doing this. I have this formula, so I have weighted formula, and I'm going to learn the weights. In both relational logistic regression and Markov logic networks, if all the R's are observed, then the probability of Q is this sigmoid that depends on the count. So there's the number of R's, it's the number of R's, the number of individuals for which R of X is true. So we get a count, so it ends up with this sigmoid. So this is what happens in both of these. The reason this is an interesting example is here are two sigmoids of degrees of polynomial 2. We'll draw them here. So one of these, so they're basically identical between 0 and 60. Right, you can't tell the difference in them. But one of them, if you look at the factor before the n squared, one of them is convex and one of them is concave. And the convex one has to go up at the end. So we're going to look in here, so the convex one has to go up. So if it goes down, it then goes up again. The other one goes down at the negative number of n, so it doesn't affect us. But this one here, so you could learn this in this left round. So extrapolation is, you have to be really careful of extrapolation, particularly if you learn in a small number of individuals and extrapolate to big ones. So before we know anything about entities, they're indistinguishable and should be treated identically. So exchangeability means names can be exchanged and the models doesn't change. So if you're Bayesian, the probability depends on what's known, right? So now we have it. So now we have the case that entities about which we have the same information must have the same probability. So if you put those two together, then you end up with saying that there's a symmetry, right? You have the entities about which have the same information. At the start, they're everything. Before we know anything, they're all got to be treated as symmetry. So this symmetry is exploited in what we call lifted inference. I'd recommend seeing Guy van den Broek's Computers and Thought lecture from IJCAI 2019. All right, let's finish up with talking about identity and existence uncertainty. So lifted inference, or inference itself, requires counting. So here's an example. Suppose in the room was Sam's mother, Chris's football coach, and a brilliant mathematician. How many people were in the room? Well, the answer is at least one, because they could be all the same person. All right. If we also specified there was no one else, there are between 1 and 3 people. As an aside, we really need knowledge graphs to be able to state, and there are no more. So we'd like to be able to state that for at least this case, the closed world assumption is not appropriate globally, but we ought to be able to state that really there are no more of these. That's all there is. All right. So we end up with this correspondence problem. We have symbols and we have entities. And we have the house with the brown roof and the tall house might be the same one, but there might be no house with a pink roof. And so if you have C symbols and I entities, there are C to the I plus 1 correspondences. There are too many correspondences, and then we want a probability distribution over it. It becomes very difficult to do that. Okay, there are ways of solving this, but it's actually a really challenging problem. And also, we end up with what's called the clarity principle. We really got probabilities over well-defined propositions. So what if an entity doesn't exist? What if there's house H4 and roof color and H4 pink and not exist? And in first order logic, this is nonsense, right? Because exists is not a predicate that's true of an object because there's no object that H4 that if it doesn't exist, okay? And the question is, what if more than one entity exists? Which one are we referring to, right? You might have a model of a house with 3 bedrooms, The houses don't come labelled with the first bedroom and the second bedroom. They might have the largest bedroom and the second largest, but then it's external to that. Okay, so here's a few ways of solving this. One way of solving it is to have a distribution over the number of entities. For each number, we're going to reason about that correspondence. And for each observation sequence, another way to do it is for each observation sequence, we're going to hypothesize its correspondence. So here's an example of this. So observe a radar blip. There's either, we're going to hypothesize it's either a false alarm or it's a plane. If we observe another blip and there's a plane before, well, the second blip could either be a false alarm, it could be the same plane or another plane. And as we go along and observe more and more things, we end up with more, because now we worry about existential, maybe this plane didn't exist. Maybe we get to hear there are 3 false alarms in a row, and that just might be very unlikely. It might be, one of these others might be more likely. We can have a probability distribution over it. So one way of solving this that I like is this idea of the first order semantic tree. We're going to split on quantified first order formulae. So we're going to have exist in X, tau of X, and it's either true or false whether this exists. So the true gives the scope of X, and the false gives a tree not in the scope of X. And this logical generative models actually generates these in a first order way that talks about, this solves the existence and the identity in a neat way that we're learning them all together. Here's the example of doing this. We're going to first of all split on whether there's an apartment. If there's no apartment, well, that's fine, there's no apartment. If there is an apartment, we can say, does it have a bedroom or not? And either it doesn't have a bedroom or it does. So this branch down, this true branch down here is the case there is an apartment and there is a bedroom in it. And then we can ask the question, does there exist a green room? And in the third here, there's a bedroom but no green room. And the fourth, there's a bedroom and a green room. And then we could talk about whether they could be the same room or they could be different rooms. So we can have now probability distributions over the description of houses, which is sort of a challenging problem for these. All right, so what's important here is that all probabilities are over well-defined first order formulae. All right, so conclusion, I've run out of time here. There's a challenge now is to model and learn uncertainty about properties of entities, relations amongst entities, how properties and relations interact, the identity or the equality of entities, the existence and number of entities, and their interactions between time, ontology, causality. So there's the challenge we have. There's still lots to do, and hopefully people will step up with the challenge. And I thought I'd finish with a quote of Bertrand Russell. What's now required is to give the greatest possible development to mathematical logic to allow the full importance of relations and to found on this as a secure basis for philosophical logic. Okay, so what I'd like to do is borrow the 100 years later Bertrand Russell's, but move into the modern era where people are talking about uncertainty and learning in complex relations. Okay, thank you all.